Chemistry 30. This is our 8th lesson in the acid-base unit. This is buffer solutions. In this lesson, we will look at buffer solutions, how our blood plasma works as a buffer regions on a pH curve, and a buffer's capacity. Buffer solutions. A buffer solution is a mixture of a weak acid and the salt of its conjugate base. They are a conjugate pair. In solution, they are usually present in relatively large and approximately equal amounts. This right here is an example of a buffer solution. H2CO3 and NaHCO3. The reason why it is the salt conjugate base is because we cannot take the ion HCO3- and place it into solution. So therefore, we have to have an ionic compound, which we can then place into the solution. Once NaHCO3 dissociates, what is really the buffer is the conjugate base, HCO3-. Buffer solutions have a specific pH due to their concentrations of the species present. They are used to calibrate pH meters and essentially control pH-sensitive reactions. A good example of a buffer is our blood plasma. When added to water, buffers protect the solution from large pH changes when acids or bases are added. You could say they maintain or stabilize the pH of a solution. In blood plasma, there is the H2CO3/HCO3- buffer system. Now this is a weak acid and its conjugate base, so therefore they act in an equilibrium system, as we can see below. We have H2CO3, which is our weak acid. It is going to react with water to form an equilibrium with the products HCO3- and H3O+. How buffers work. Determine the Bronsted-Lowry reaction when NaOH, a strong base, is added to the H2CO3 NaHCO3 buffer solution. Are the reactants or products favored? Pause the video and attempt this example. To determine the Bronsted-Lowry reaction, we first have to list all of the species available to react and determine our strongest acid and our strongest base. They will then become the reactants. Our strongest acid is H2CO3 and our strongest base is OH-. We then transfer the hydrogen from the acid to the base to form the products. Since the acid is vertically higher than the base on the table of relative strengths in the Chemistry 30 data booklet, this is going to be a product favored reaction, meaning the products will be greater than 50%. Since the forward reaction is favored, the conjugate acid reacts with most of the OH- to become products. Since we are then limiting the amount of OH- in the equilibrium, the pH of the overall system will not be greatly affected. Let's proceed with another Bronsted-Lowry reaction, but now let's add a strong acid, HCl. Pause the video and attempt this example. Again, we have to list all of our species available to react. Remember, HCl is a strong acid, so we break it apart into H3O+ and its anion, Cl-. We then have to choose our strongest acid, which is H3O+, and our strongest base, which is HCO3-. Those will then become the reactants. We will transfer the hydrogen from the acid to the base to form the products. Since the acid is vertically higher than the base in our relative strengths of acids and bases table, this again will be a product favored reaction, meaning the products will be greater than 50%. As a result, the forward reaction is favored. The conjugate base will react with most of the H3O+ to become products. Therefore, we are going to limit the amount of H3O+ in the equilibrium system, and the pH will not be greatly affected. Buffer region. This is where the pH of a solution resists any change when an acid or a base is added. It is a region where both the weak acid and its conjugate base exist. Halfway to the equivalence point, the weak acid and conjugate base are at approximately equal amounts. This would be a buffer region. If we look at our pH curve below, we have two buffer regions, and they are the regions right before the equivalence points, where the solution resists any drastic pH changes. Just to point out, at the very end of the curve, this is no longer a buffer region, and that is because there is no longer any of the weak acid remaining. It is only its conjugate base. Example number 1. Circle the buffer regions on the following titration curve. Pause the video and attempt this example. In this first example, in our pH curve, we have two equivalence points, right here and right here. Remember, a buffer region occurs before the equivalence point. So therefore, in this pH curve, we have two buffer regions, one here before the first equivalence point and one right here just before the second equivalence point. Example number 2. Which of the following chemical species could act as a buffer? Pause the video and attempt this example. Remember, a buffer is a weak acid and its conjugate base. So right away, options A and D cannot be valid. HClO4 is a strong acid and HBr is also a strong acid. If we look at option B, we have NaOH and NaHCOO. They are not conjugates, so therefore this can also not be a buffer. Therefore, as a result, the buffer is HOCl, which is a weak acid, and the salt of its conjugate base, NaOCl. Buffer capacity is a buffer's limit to resist a significant change in pH. Once either of the weak acid or the conjugate base pair is completely consumed, adding more of an acid or a base will cause the buffer to completely fail, and the pH of the solution will then drastically change. The amount of acid/base added must be less than the amount of buffer present in the solution. This is why the pH curve has a shallow plateau and there is a sudden sharp rise when the reaction progresses. And that is all for the acid and base unit. Moving forward, we will write the acid-base unit test and explore redox reactions.